Okay, good morning. So what we're going to look at today are cones. Now, cones is a shortened down version of the full name of what a cone actually is. The full name on a cone, they're called right circular cone. That's the full name. So this really is kind of an abbreviated version of what the full name is. Now, the full name gives you an awful lot more information about the cone. So if we think about, so we have this right, okay, and then circular as well. So if we look at a cone, so what we're looking at here, so this is a cone here. Okay, so we can see that we have, let's think about the parts that we have. Okay, so you have the radius, and if we look at this little, we have a radius which roughly goes across here. Okay, so that's the radius. So the underside or the surface area of the underside of a cone is a circle. Then if we think about what we have, then we have, if you like, this kind of, okay, so this is going down the page. You have what is known as the length, the slant length. Okay, so that's like the L, the slant length. So that kind of goes down the slant. And then if you're to go inside the cone, okay, and then draw a line right down to the radius, what you're going to have then is the height, and this is what's known as the perpendicular height. So these are so you have the radius, you have the slant length, and then inside then you have what's known as the perpendicular height. And again, you can kind of see it better here in this diagram here. So you have the radius along the bottom, you have the slant length, and then inside then you have the perpendicular height. So the circular part in the name comes from the circle. The underneath of a cone is a circle, and the right part comes from in here. And we'll just have a look in here. So what you'll notice that when you look inside, so if you take the height and you draw a line down from the tip of the cone down to the bottom, down to where the radius is, you have this um, right angle being formed here. So you have a 90-degree angle here. Okay, so that's a right angle, and it's at 90 degrees. So you have then what's known as Pythagoras' theorem. So if you remember this, so Pythagoras' theorem. So what does Pythagoras' theorem state? So O-R-E-N. So Pythagoras' theorem. So basically what Pythagoras' theorem says is that, so imagine this is side A, this is side B, and this is side C, the lengths. So what it says is that the A squared is going to be equal to B squared plus C squared. So what that means is that the length here, so this length here, is going to be equal to this length here squared plus this length here squared. So the length here squared is equal to this length squared and this length squared. So what we can do then is, what we can say then, another way we can say is that in relation to the circle and in relation to the cone, and then in relation to the dimensions of the cone, we can say that the length squared, which is this, is equal to the height squared plus the radius squared. So what we can do is we can take this Pythagoras' theorem and we can apply it to the cone. So we can in this way here. So this here is what applies to the cone. So the length is the length here, is the slant length of the cone, the height is the height here, and the radius is the radius here. And again, this is a 90-degree angle, so therefore it's known as a right angle. So 90-degree angle, which is a right angle. So this is where the name comes from then. If we think about the name in relation to this cone, that's where we get the name from. So it's known as a right circular cone. So again, like Pythagoras' theorem applies here, as we've seen. Now, if we take then, so what we want to kind of look at then is what's known as, so just like we've looked at with the rest of them. So we want the curved surface area. Okay, so the curved surface area is going to be, if you're to take this cone here and you're to make a net like what we see there. So imagine you're to take this cone and you're to make a net, so you're to split it out. This is what we have here. Okay, so this here is going to be, this area here is going to be what's known as the curved surface area. So the curved surface area then, so we need to have a formula for the curved surface area. So the formula for the curved surface area is equal to pi or pi length. Okay, so that's our formula, and that gets us the curved surface area. So the next thing then that we want to look at is what's known as so we have the curved surface area, but then we want to kind of think about the total surface area. So the total surface area. So and we can just abbreviate this TSA, which is total surface area. So again, the total surface area is going to be this, okay, plus this, the area of both of these. So again, so this is just a net of this. Okay, so this here is a net of that. So the total surface area is going to be, we're going to use this part. So you're going to have pi r by length, plus you also want to get the area of the circle, okay, or the underside of the cone. So you want to get the area of this underside of the cone as well. And we know that the area of a circle is just pi r squared. So it's going to be pi r squared. So again, these are your two formulas. And these formulas will generally be in your maths logs book as well. So you don't need to generally be learning these off, but it is important that you know how to use them and that you know how to manipulate them as well, so that if you're given some or part of the parameters, that you're able to figure out and work out the other parameters from it. So the last piece then, what we want to kind of think about then is the volume. So we want to kind of think about the volume of, how do we get the volume of a cone. Now, if we have a look here, so Archimedes, okay, so he was a Greek mathematician. He done a lot of the foundation work in relation to geometry. So what he found was that if you were to take the volume of a prism, like for example, like this cube that we have here. So we have this cube here, okay? or we can just call it a prism. So we can call it a prism. So, and what he found was that if you were to take a pyramid, okay, so let's say something like this here. So we have a pyramid here. So you can see, so we have a pyramid. If you were to take this, so just bear with me one sec. And you were to take this pyramid and you were to fit it inside, let's say, inside the prism. So you had a prism that could encapsulate the whole pyramid, yeah? So the pyramid was able to just fit inside it perfectly. So from top to bottom, left to right, back to front. What he found was that the volume, so let's say if the volume of this prism was, let's say we'll just make up a number. So let's say the volume of this prism was 15 centimeters cubed, then the volume of the pyramid that fits into this perfectly is going to be 1/3 of this. So it's going to be equal to 5 centimeters cubed. So what he found was that basically the volume, so the volume of this would be 1/3 the volume of the prism that is fitted into. So for example, like this. So this, if you were to fit this in here, like so, what would happen? Let me just this so we can. Okay, so it fits in there perfectly. So basically, so let's say if your cube was 15 centimeters cubed, this is the prism, let's say the cube, and then you took your pyramid and were able to fit that inside there perfectly, like so. So it's not quite just in. Okay, so there we go. So it's perfectly in there. What he found was that the volume of the pyramid was actually going to be 1/3 the volume of the prism or the cube. So if you were to look at it like this, so basically if the volume of this here is 15 cubic centimeters and this pyramid fits inside it perfectly, then the volume of the pyramid is going to be 5 centimeters, which is 1/3 of 15. So this was a principle or an observation that Archimedes made. Now the same principle holds true as well for cones. So if you were to take, for example, so we have a cylinder here, and again, so let's say the cylinder was 15 centimeters cubed. So and you were to take your cone, and that cone fits perfectly inside it, like so. Okay, so that cone, you can see there that it fits perfectly inside it. So you can just put it inside of it. I'll just take this out. Again, what he found was that if, let's say, if the cone was 15 centimeters, then, sorry, if the cylinder was 15 centimeters cubed, that was the volume or its capacity, then the capacity of the cone was going to be 1/3 of that. So 1/3 of 15 is equal to 5 cubic centimeters. So therefore the volume of this will be 5 centimeters. Okay, we're going to just try it up here. So it's going to be equal to 5 centimeters cubed. Okay, so it's basically this, it's going to be 1/3 of this. So what we can do is we can use this principle then, and we can come up with a formula to work out the volume of a cone. So the volume of a cone then is going to be equal to 1/3 the volume of a cylinder. Now, if we remember, the volume of a cylinder was just pi. So it's just equal to pi r squared by height. So this part here relates to the volume of a cylinder, okay, and then this part here relates to this principle that basically if the volume of your cylinder is 15 centimeters cubed and you have a cone that fits perfectly inside that, and also as well, like these will have the same, they'll have the same size base as well. Okay, so if you like, the radiuses down here are going to be the same as well. So let's say this radius here and this radius here, they're going to be the same. So as a result of that, what that means is that if this is 15 cubic centimeters, then the cone is going to be 1/3 the volume of this, which will be 5 centimeters cubed. So that's the principle here. So this is the formula then. This is the other formula that you need to know. You need to know how to use it. It's the volume, how you work out the volume of a cone. So there are three formulas. So you have the curved surface area, the total surface area, and then the volume of a cone. Okay, so let's work through an example then. So we have this question here. So a solid cone has a vertical height of 6 centimeters. So that's its height, vertical height here. And its slant height then, which is this here, of 7.5 centimeters. Find the radius of its base. So you want to try and find the radius here. Now what we can do is we can use Pythagoras' theorem. So remember, Pythagoras' theorem, what's it going to say? We have a right angle like this. Basically what is going to happen is, so let's say this is, so a squared. Okay, actually, so a, let's say, has length a, b, and c. So therefore a squared is going to be equal to b squared plus c squared. So that's Pythagoras' theorem. So what we can do is we can use this to figure out what the radius is. So what we're saying is, with this triangle in relation to the cone, A is equal to 7.5 centimeters. C is equal to the radius, which is unknown, which is what we want to find out. And then B is equal to 6 centimeters. So what we can do is we can substitute in the values that we have here. So, and we can use this then and manipulate the formula. So what we're saying is that 7.5 to be squared, okay, that's coming from the A up here, is equal to B squared, which is 6 to be squared, plus C squared. So actually we might just change that and make it equal to R to be squared, and this is what we're trying to figure out. So we can work this one out. So what we can say is that, so let's work out, so 7.5 to be squared. Let's get our calculator. So clear this. So 7.5 to be squared is equal to 56.25. So let's just write that. So 56.25, 56.25 is equal to 6 squared. So 6 squared is equal to 36. Equal to 36 plus r squared. So now what we're trying to do is we're trying to get this r squared on its own. So what we have to do is we have to get rid of the numbers around it. So this is plus 36, so we can minus 36 from this side. If we minus 36 from this side, we have to minus 36 from this side as well. So what will happen is these two will cancel out, and then I'm just going to write this over here. So therefore r squared is going to be equal to 56.25 minus 36. What's that equal to? Okay, so 56.25 minus 36, which is equal to 20.25. So therefore that's equal to 20.25. So now what we want to do is we want to get rid of, so we have r squared here, but we want this just to be r. So if you take, like, the opposite of a power is a square. So if you have, so what you need to do is, in order to get rid of this power up here, you need to square this. Okay, so you square it, and that will just get rid of the power and just leave you with r. Now if you square one side, you have to square the other side as well, like so. So then that would be r will be equal to the square root of 20.25. So let's have a look and see what that is. So 20.25 to be squared is equal to 4.5. So therefore that's equal to 4. So it's equal to 4.5. Okay, so that's the radius. The radius is 4.5. So it's 4.5 centimeters. Okay, so we figured out what the radius is. The radius is 4.5 centimeters. So what's the next part? So find the radius. So find the total surface area in centimeters, in centimeters squared, and give your answer correct 3 significant figures. Okay, so let's try and work through that part. Let's change the color. So the total surface, so find the total surface area. So let's think about what the total surface area is. So the total surface area is going to be this curved surface area of the cone plus the surface area of the circular base. So what's that going to be equal to? So the area, so we just use our formula, area is going to be equal to pi r by length. So that's the curve of the cone, the curved surface area of the cone, plus pi r squared, which is the surface area of the underside of the cone. So then what we can do is we can use this and we can substitute in the values that we have. So what have we got? So we've worked out this is the radius. So we have the radius, and we have, so that's the radius. We have the length, which is this up here, 7.5. And what else does it look for? So radius, length, and radius. Okay, so we have everything that we need in order to be able to use this formula. So we just substitute in the values that we have. So therefore this is going to be equal to pi times r, which is 4.5, times the length, which is 7.5, plus pi times the radius, which is 4.5, to be squared. So then what we can do is we can work out these parts. So if we take pi, so let's just clear this. So pi multiplied by 4.5, sorry, is equal to, and then multiplied by 7.5. So it's equal to 106. So let's say, so 106.02. We'll just say this is 106.02 plus, so 4 to be squared, 4.5 to be squared. So let's clear this. So you have 4.5 to be squared, which is 20.25, and then multiply that by pi, which is equal to 63.61 plus 63.61. 63.61, and then if we add these together, 63.61 plus 106.02, so it's equal to 169.63. So that's when we add these two together. And what does it ask us? So it says give your answer correct to 3 significant figures. So if we so let's say the 1 is the first, 2 is the second, and 9 is the third significant figure. So we're keeping these first 3 significant figures, and then we look at the number afterwards. If the number afterwards is greater than 5, then we round it up. So 169 will become 170. So this is going to be equal to 170. So this is the volume. Sorry, this is the total surface area. So therefore, if it's surface area, it's going to be in centimeters squared. So they're the types of questions that you could be asked in relation to this particular type of problem. So, okay, so I think that's everything. So we've looked at the volume. This is your volume. We've looked at total surface area, which the calculation we've done is that. We looked at the curved surface area, which is the surface of the curve. The full name is a right circular cone. The reason it's a right circular cone is because the perpendicular height and the radius form a right angle triangle, and then therefore it follows Pythagoras' theorem, like what we've worked out here. Okay, so I think that is everything. So hopefully that made sense. And what I'll do is I'll put up some questions for you that you can work on. Okay, thanks guys.